to thank our facilitators for always keeping up with us and for very, very informative lessons. And with that, I would like to hand over to our facilitators, Dr. Helen and Dr. Odom. Over to you. Thank you.
Hello, good afternoon. I hope everyone is hearing me properly.
Yes, we can hear you very well. Good
afternoon. Thank you. Yeah, so I think we are going to start off straight away. We see 144, 45. So we should be able to. So I hope what we had yesterday added some values to the participant. So yesterday we ended up when we were looking at the different models, how to choose a model. So today we are going to try to see some of the models. So the first thing I'm going to do is I'm going to introduce the models from the perspective of experimental design. Just briefly, I'm not going to talk about experimental design that much. So I know not everybody does experiment, but at least a number of you probably have done experiment one way or the other. And as the students, you need to design a suitable experiment if you are to get good results. So we know that experiments are the only sure way to establish cause-effect relationship. So if you want to determine whether one factor causes some kind of response in the system, the best way would be to set up an experiment, or as we saw yesterday, it could also be if you can do kind of a longitudinal study over a long period of time, you follow a certain group of people over time. So it doesn't matter which field you are in, the principles of experimental design will always be the same. And these are the three principles of experimental design. I think, let me just get my pen. So we're going to look briefly at replication. So those who do sampling survey, replication as equivalent to what we call sample size. We also have the second principle, which is called blocking. Blocking is related to stratification for those who do sampling survey. And then we have the process randomization, which is also same with randomization or random sampling in the case of sampling survey. So for those who do field experimentation, you always have to see you plan your experiments in what we call plots. And then depending on the setup in your experiment, people can either believe your results or not, or you can either detect the differences that you set out to find out, or you fail to detect, depending on how you set up the experiment. So the principles of experimental design that we're going to look at briefly will determine whether you're going to have a good outcome or not when you're going to set up an experiment. So there are two things we talked about yesterday. We talked about the response, and then we talked about the predictors or the explanatory variables. So in terms of the experimental design, we are mainly interested in two components. There is what we call the material, the experimental material that you're going to use. So this depends entirely on the type of experiments that you do. If you are a plant scientist, for example, your experiment can be done on a plot of land. It can be done in a pot. If you are an animal scientist, your experiment may be done on animals. If you are a social scientist, you could use subjects, maybe school children, maybe youth, depending on the objective of your study. So there are two things. So you need to determine what is your experimental material. And then the other thing is also the kind of what is the treatment set. So the treatment in this case is what you're setting out to actually go and compare. So for example, the treatment is in animal studies, for example, you're comparing drugs, maybe you're comparing different feeds, maybe in human studies, for example, there's a lot of experiment that goes on in psychology, where maybe you look at the response of people to certain stimuli or response to some kind of, in medicine, you also have the issues of drugs. So from the perspective of an experiment, we have what called the treatments. So the treatments is mainly your explanatory variables, what you want to find the effect of. While the experimental material here is the treatment is applied on this material, and then we observe the response. The response can be maybe the weight gain in animals. It could be milk yield. It could be how fast somebody responds to a certain situation. So you could also have something like you comparing different varieties of tomatoes. And your experimental material could be, you have nicely prepared pots where you're going to plant your experiment. So here, when you're dealing with the experimental material or the experimental unit, mainly the key interest is how do we control variation that we are not interested in studying. We are interested in comparing treatments. So let's say we are interested in comparing these different varieties of tomatoes. But if you don't get soil that are uniform, you don't water uniformly, that can actually cause problems as far as the relationship you're trying to study is concerned. So you need to be able to identify your experimental material and then your treatments. That is very key. And then later you can look at the response. The response mainly what you measure after setting up an experiment. Okay, so you could also, your experimental material could also be a plot of land, like what we have here. You still have the same treatment, but in this case now you are you're going to do your experiments on a plot of land. So you can see in this case it's easier to control variation in the pots compared to in the field. So in the field, there are lots of issues that you need to take into consideration, which include maybe things like the slope, maybe soil fertility, variation, maybe there are shadings and so on and so forth. So those are the things that needs to be taken into consideration. When you set up your experiment finally, it's important that you know the response that you're going to measure, the response variable that you're going to measure finally. And the interest in most cases is we want to see the effect of the treatment on the variable, on the variables. So the treatment here will try to explain the variable. So here we can look at things like plant height, number of copes, maybe leaf length, number of leaves, and so on and so forth. So it's very, very critical that you understand the languages so that later on when we are coming to set up our model, then that means we will understand exactly how the system. Remember yesterday we said the type of variables, the response variable will determine how the choice of the model. So you need to know for your experiment which are the variable that you're measuring as a response to the treatment. The treatment itself also can have different characteristics. You can look at fertilizer, for example, which is in quantity, or you can also look at pesticide, which could be in quantity, but you could also look at variety, which is purely categorical. You either have variety A, B, C, or D. So when you finally set up to do your experiment, there are basically two things you're interested in. You're interested in comparing the treatments. So let's say in this case, we want to compare two types of energy drinks. We have this Monster Energy, and then you have Red Bull. Now, this is your treatment, and this is your experimental material. So you can see that the choice of your experimental material may actually have effect on how you're going to do your comparison. So here we have two different scenarios. We have in the first case where we have a small, maybe a child trying to wrestle with an adult samurai. So you can see in this case that because the experimental units are not uniform, whatever result that is going to come out of this experiment is likely going to be questionable. Because at the end of the day, we are not going to be sure whether it is the effect of the energy drink or it is the differences in the experimental units. So we are going to see how do we design an experiment in such a way that you avoid what we call confounding. So with confounding, in this case is that you cannot differentiate whether the effect you are seeing is as a result of the treatment that you have applied or it is as a result of the differences in the experimental material. So this side probably gives us a much better comparison because at least you say that the two gentlemen are matched in terms of maybe the size, in terms of the age, and therefore any differences that you're going to observe between the two of them is likely due to the differences between the energy drink. So the main thing here is that we need to be able to make comparison control. The other thing is we're also interested in measuring what we call experimental error variance. So experimental error is simply variation between similar experimental unit receiving the same treatment. So here, let's say we have experimental unit 1, 2, 3, and 4. We are all giving them the same treatment. So this variation that we observe here, we have 10, we have 9.5, we have 11, we have 9. So this variation here, we can attribute it to what we call experimental error variance. But when we look at the other side of things here, if you look at this side here, we find out that now, although the treatments are all the same, but the experimental materials are not the same. So if the experimental materials are not the same, that means part of the variation that we observe here is going to be due to experimental error, and part of it is going to be due to something else, which is related to the differences in your experimental material. So the principles of experimental design will guide us to design a suitable experiment so that you're able to estimate the two things I talked about without any bias. Okay, so so these are the principles for experimental design. The first one is replication. I'm just going to touch on it very briefly. So what is replication? So replication is simply repeating a treatment under identical condition in an experiment. And the key word here is that each treatment is applied independently to two or more experimental units. So you can see here we have so this is your experimental unit 1, experimental unit 2, experimental unit 3, experimental unit 4. So you can see that the treatment is applied independently. This application is independent of this application which is independent of this application, which is independent of this application. Okay, but when you look on this side, for example, then you'll see that these applications are not independent. You have rat number 1, rat number 2, number 3, number 4, and so on and so forth. So here, you cannot take each rat to be a replicate because the treatment has not been applied independently. So there are also issues. I see okay, Brian, can you put the question in the Q&A? Then my colleagues will try to answer that. I'm going to just give a brief introduction, and then we are going to go to ARA, and then we're going to run some models, and then we are going to see what we are talking about here. Yes, Brian, you raise your hand. Can you type in the chat? My colleagues should be able to answer, but if you feel people will benefit from your question, then you can put it in the, I can answer it straight away. Okay, so if you work in the lab, there is a difference, what we call a biological replicate, and then there's also what we call a technical replicate. So in the lab, always, you don't run a sample only once. So in most cases, if you prepare a sample from leaf A, you can break it up into A1, A2. So this would be kind of repeating treatment A, but is leaf A, but it's not a biological. It's not a biological. This is a technical replication because it comes from one biological sample. So A and B are two separate biological replication. That is what we have there. So the other thing is what we call blocking. So remember when we started looking at this experiment at this point here, let me first erase. So we can see that as much as we are interested in comparing our treatment, no, but we also have variation that is not our treatment. Okay, our experimental units are not uniform, and that certainly is going to cause us a bit of problem. So here, if you don't control for this non-treatment variation, it's likely to do what called confounding the effect of the treatment. So let's say you are doing some kind of maybe a psychology. I mean, maybe you're doing psychology or something, or you're trying to look at motivation. So let's say you want to test the effect of 2 management strategies. These are your treatment on productivity of employee. Now you can see here that this group of employees here. These are people who are completely different from this group here. So if I say, for example, that I'm going to put management strategy A here, and I'm going to compare with management strategy B, you actually realize now that apart from the differences in the strategy that we are going to compare, but the experimental materials are also completely different. This group is younger, they look at the world very differently. This group is older, they look at the world also in a very different way. So at the end of the day, if we find a difference between treatment A and treatment B, it becomes questionable, or you begin to question, is it really because the treatments are the one that is working, or simply because we're just dealing with two different group of people who will differ anyway? So here, if let's say we're interested in comparing these different types of bonds. Now, if we say, okay, let this type go to this dog here, this type go to this dog here, that type goes to that dog here, and then this one goes to that dog here. Now, because the dogs are fairly uniform in terms of age, maybe breed, strength, and health-wise. So if we observe any difference between A, B, C, and D, likely we are going to attribute these differences to be due to the nature of the bonds, but not due to the differences between the dogs. But if you do it, if you look at this group here, then the story is going to change. If you give this dog this, the other one receives that, this other one receives that, and then the big one receives that, it becomes a little bit difficult for you. For example, let's say we are measuring how long it takes for a particular bone to be cracked, and that could be how strong the bone is. But then these small puppies here are likely not to, even if you give them chicken bones, they're not likely to crack it. So it doesn't mean that if they take 2 hours trying to play with chicken bone to crack, it doesn't mean that chicken bone is stronger than a cow bone. It just simply means that you're trying to compare dogs that are different in terms of characteristics. So it ends up you end up comparing more of your material than actually comparing the treatment itself. In the field, we also have situations where, let's say, you have plots that are very close to the line of the trees here. So as you can see from here, we see that there's a bit of shading within here. And then compared to the ones that are far. So in this case also, we need to take this into consideration when we are designing our experiment and we do what we call blocking. So what is a block? A block is simply a group of experimental units that are considered to be homogeneous. Okay, so yes, I think somebody raised the people are raising hands. I don't know. Yeah, my colleagues should type in the Q&A. My colleagues will be able to answer that. We are also going to get time for questions, for some questions. So we are also planning to have a Q&A session and experimental design in the near future as part of RUFORUM activities. So maybe within this week, we are going to request each one of you to at least get some, if you have questions that need to be answered regarding experimental design, we are going to give you the contacts, you're going to send it to us. And once we compile this question, then we agree on a day that will inform members so that we can come specifically to answer questions that are related to experimental design. Okay, so a block are simply groups of experimental units that are expected to be similar. So this is one block, for example, because you have similar dogs here. This could be another group block. If you're doing human study, you could block using age. So you have older people, and then you have the Gen Zs as another group of people. So this certainly then becomes a little bit easier to handle compared to have to that. So if I bring my experiments where I'm trying to compare the different types of bonds, then I can easily test my bonds within this group. I can test my bonds within this group. I can test my bonds within this group. I can test my bonds within this group. And then I can combine the results from all this, and then I should be able to get a better result than if I did not use blocking. So in the field, we can see things that looks like this. These are also examples of blocking in the field. And then randomization is simply the process of assigning treatments to different experimental units using mostly what called non-well understood probability scheme. So here, each treatment is supposed to have an equal chance of ending up on any experimental unit. And we do randomization because we want to have biased estimates of the experimental error variance. which will give us validity of the study. So this is briefly on the principles of experimental design. Now we use the principles of experimental design to categorize the different designs that we have. So for those who do experiments, we have a number of design. I'm just going to talk about what we call the standard one. So the first design is what we call completely randomized design, those which you call the CRD. So with the CRD, the main assumption here is that your experimental materials are homogeneous. So as you can see from here that all the dogs are actually very similar. So if I'm going to give this dog treatment A, I give this dog treatment A, I give that dog treatment A. Now, if I get, like say we get a value of 10 here, maybe you get a value of 8 there, you get a value of maybe 12 there. Now, this variation here will be what we call our experimental error. Okay, so if let's say we give this a B, we give this a B, maybe this one gets a C. So here you can see that we can compare our treatments without actually worrying about the dogs, because the dogs are very uniform. But in nature, it's rare that you can have experimental unit that are uniform. Maybe if you're working in the laboratory, you can have uniform experimental unit. But mainly if you work in the field, it becomes a little bit difficult to get to situation. We can also have, we can do in the pots. So the pots are uniform. You can have, maybe if you have chicks from the same N, they are uniform in terms of age, in terms of maybe breed. And if in the lab, generally, you can control the conditions. So here you can use your completely randomized design. Okay, so here we can see that we have uniform rats, and then we have different treatment. You have treatment A, B is here, first treatment B, second treatment B, third treatment B, and the fourth treatment B. So here we have treatment B is occurring 4 times. And if each treatment is applied independently, then in this case, we are saying we have 4 replications for treatment A. Treatment B, we also have 4 replications for treatment A, C, and A, B, and C. So why am I talking about this, and how do we relate this to the model? We relate this to the model because it will determine the relationship between the response variables and the predictor and the treatment. Now, so for a completely randomized design, we have a different model. Now, when we bring in the issue of blocking, that we also have a different model. If you bring in another blocking, then you'll have a different model. So I'm going to show you the different types of models for the different design that we are going to, and then we are going to go to ARA, and then we are going to run these different models, and we are going to see the effect of choice of a model on the results of the analysis. So, for example, yesterday we talked about having a situation where you think there should be some predictors may be missing in your model. So we are going to see the effect if you have a predictor that is missing in the model. What's likely to be the effect of that? But we know that in nature, it's very, very unlikely that you're going to get very uniform experimental unit. Even those who work in the lab, they breed rats specifically to do experiments. So in most cases, you can assume there's some kind of homogeneity. But if you go on practical, you go practically to the farmer's field, for example, if you're an animal scientist, I mean, if you say, okay, the farmer should give you the animal for experiment, so you may get animals that look like this on one farm. You may get another set that looks like this on another farm. You can get this on another farm. You can get this on another farm. You can get this on another farm or that on another farm. So assuming that the experimental unit is homogeneous is likely not going to be tenable in this particular case. So we need then a design that will take into consideration the fact that we have different experimental units. So we then bring in the issue of the blocks. So in the case of our rats here, we have what we call completely randomized design because all the experimental units are quite uniform. So the randomized complete block design, in this case, we group our experimental unit into blocks. So here, for example, we have one block. Here you have another block. Here you have another block. And then here you have another block. So then I can compare my treatments here. Maybe I give this one an A, another one gets a B, another one gets a C, another one gets a D, another one gets a E. Then I go here, I also do the same, A up to E, I go do the same, I go do the same. So in this case here, we are talking about a block being complete in the sense that all the treatment will occur in each and every block. We also have what we call incomplete block design. So with incomplete block design, the whole thing here is that you may have very many treatment and you don't have enough experimental unit that are homogeneous. So in that case, what will happen within that you can have a block that has fewer treatment than the total sets that you have for your experiment. This is the last design that I'm going to describe. After this, then we can go over and start running. So, okay, I just say something, okay, how can you design an experiment and ensure measurements are randomized when looking for the impact of lions as a carnivore on plant diversity in an ecosystem? Yeah, this becomes a little bit, the question is, Boaz, the question is, in this case, do you think, are we doing an experiment or not experiment? Because how much can you control? Are you able to say, okay, let's say, for example, you partition a section with park, and then in some section, you put a carnivorous like a lion, in some section, you don't put carnivorous, and then you monitor diversity over a period of time. Now, you find this is a little bit, this may be a bit of a challenge. What you could do is you could probably do some kind of, you could do, maybe what you could do if you have areas with different numbers of carnivorous, you could try to follow that over a period of time, but that becomes more what we call a pseudo experiment. Okay, so I think that's some say I have 3 treatment with replicate and I happen to lose 2 replicate within the same treatment. How can I handle the data of that treatment? Well, you can still handle the data with the treatment in that you can consider some of these observations to be missing. Boniface, you're raising your hand. Can you type your question? Or can the host allow Boniface to say something? The drive has been shared. I think they will keep on being shared. Yes, boss.
Yeah, thank you very much, Dr. Thomas. Yes, a very good response I got from you, but the question was like if we have to reintroduce lions in the area where they were not present, and we want to measure if the plant diversity will be improved by means of the number of herbivores that will be present at that time and after introduction of the lions, and then of course we'll be measuring on a plant diversity. How can we design the way on how we'll collect data and do our measurements? Because the problem is we want to randomize and ensure like you don't have any biasness, and of course we keep some factors constant and avoid confounding effect. So this is what I want to get clarification. I know it's not going to be a real experiment, but if we were to introduce lions to the area where they were not present.
Well, it is a bit of a challenge here is that it's difficult to control lion present as a treatment unless you are able to partition maybe the area of the park in two sections that you fence them off, and then you can randomly decide where the lion can be reintroduced and where the lion is absent. And it's difficult in that sense. It can be easy with grazing, like grazing goats or grazing cows, because that is easy to. So if it is possible for you to actually partition the areas, and you have a way of preventing the lions from passing on to another area, then you can do that. But it will be kind of a long-term study, because you know for sure that it's not going to the effect is not going to be felt within a short period of time. So these are typical studies that could be done using, you could do some longitudinal survey or follow-up of the different areas, but you can do some pseudo experiment. The pseudo experiment in this case is that you may not be able to do randomization in certain areas. So you can just say, well, the data is the thing is assigned in this area, and you assume. But remember, randomization is one of the criteria for you to have an experiment. Yeah, I think that's what I can say for now.
Okay, thank you very much.
Okay. Any other burning question?
Thomas, in the Q&A, please.
Okay. I said I joined a few minutes late. I'm not sure if split plot is already covered. No, the split plot is not covered. What I'm trying to do for now is we want to introduce the models, and we want to do the models for the different designs. So what I'm trying to do in this case is I'm trying to bring in the situation of how do we look at the different sources of variability, how will that enter into the model. So as I indicated earlier on, we are planning to have a Q&A session for experimental design. We are going to give you the contact email where you're going to send your questions. And once we get the question, we compile the questions. We are going to be able to provide answers probably one afternoon or one evening for those who be interested in experimental design. And we plan to do this from time to time. I said if one researcher requires collecting sample from farmers field that do not have homogeneity of variety, would randomize? No, if you're collecting sampling, if you're doing sampling, you're more or less doing a survey. You're not doing an experiment. An experiment would necessitate that you set up, you have a lot more control. What you could do in this particular case would be, if you have a field with different varieties of citrus, like you're trying to put in here, the only thing would then be to have a situation where you could do some kind of splitting. So if you already have different sections with different varieties and you want to impose another treatment, then the variety could act as the main plot, and then you could impose another sets of treatment on the main plot by dividing it into subplots, and that will constitute what we call an experiment design. Okay, the last one, Gerard.
Yes, good afternoon, Doctor. Glad to take us through these basic experimental design procedures. I've already written my question there, but I need two inquiries from you. First and foremost is I'm a student of MSc. I intend to have this type of random design for evaluating feed formulation using BSF for fish in situ. Then too, also there are cases where we are supposed to state the hypothesis for these multiple randomized designs. How do we go about it? That's my inquiry to you for today. Thanks a lot.
Yeah, we are going to we will mention hypothesis as we move along. The design for now, what I would do come in is that the first thing is you need to make sure you know what your treatments are. So if you know what your treatments are, the next thing is you need to know what your experimental materials. Now, if I know my experimental material, the question that I always ask myself is, do I have a uniform experimental material? If I have a uniform experimental material, then I should be able to use completely randomized design. If the experimental materials are not uniform, but I can divide my experimental material into different blocks, then I can use a randomized complete block design under a certain condition. If I need to block in two conditions, we're going to see what a Latin square is. We're going to provide for you some additional information on experimental design, maybe along the way. But as I also indicated that we're going to give you an email address where we expect that you send your question regarding experimental design so that we are able to answer them. For one session, we are going to pick one session where we're going to sit and discuss the different questions relating to the experimental design. Okay, so let's first proceed a little bit. Okay, so what we have here is that in a Latin square, the experimenter is interested in controlling two sources, external sources of variation. So the first thing is that the design, whether it's a Latin square or a randomized complete block design or completely randomized design, it mainly involves how the experimental units are handled. It has nothing to do with the treatment. We assume you have your treatment that you want to compare, but then you want to compare this using some material. And part of the problem could be that those materials are not uniform, and that non-uniformity is likely to have an effect on the comparison. If I go back to where we started from, okay, so we have two treatments that we want to compare here. Okay, we want to compare this versus that. This is very clear. That's your treatment. It has to be well defined. Your hypotheses are going to be related to this treatment. So maybe you can hypothesize in this case is that if before you go to do research, you could say because Red Bull has a certain content, it should be able to give energy a certain, I mean, if you can say, let's say, for example, we can hypothesize in this case that the person who will take Red Bull is likely to defeat the one taking the Monster Energy because of maybe the content and maybe the amount of energy that is in. That is so the hypothesis is related entirely to the hypothesis is related entirely to the treatment that you're trying to compare. The design is related to this, the material. If I have my experimental unit that are uniform, then I will go for what we call the CRD. I don't need to worry about the variation among experimental units because they are uniform. If I have experimental units that are not uniform, then I need to do some kind of blocking. So I go for randomized complete block design. That would be what I will have in that case, okay? Now, if I'm going to define to the block, because in this case, I'm blocking using the size. So what we'll do in this case, I'll get people who are small, put them in their own group. I get people who are big, put them in their own group. Then I can compare my treatment in the group of the people who are big, and I can compare my treatment in the group that are consisting of small people. So that is what we have here. So the treatment should be very clear. What's your treatment? What's your experimental material? And then the other thing would be the response then. So the response is the effect of the treatment. So in this case, let's say, for example, the response would be who will defeat the other one. That could be the response. So you need to, who is the winner? You need the winning is the response. Is the response of taking the energy drink. But we don't want the relation between the energy drink and winning. We don't want it to be confounded by the differences in the material. So we need to design an experiment in such a way that you take care of the variation in the experimental material. Okay, so for Latin square, the thing here, instead of having only one blocking factor, we could have two sources of variation which we want to block with. So if you go to, you're given a plot of land where you want to do your experiment, then you may have variation in fertility gradients. You may also have variation in the slope. So you can only control, you need to control the two sources. You need to control for this, you need to control for that. But the treatment that you're comparing are these, A, B, C, and D. Those are the treatment that you're trying to compare. You're trying to remove the effect of the gradient, you're trying to remove the effect of the fertility gradient, and then the slope itself. So in that case, once you have two factors to control, then you have what we call our Latin square design. So this is how it look like. So let's say, for example, you may have, let's say you may have some trees along here. So with the trees here, then you can see that the plots that are closer to the tree will be highly shaded. The ones that are far away from the tree will be less shaded. Now, if you in the same field, you also have variation from low to high fertility gradients. So you use both the tree shading and then the fertility gradients to block your experiment. Then you have what's called a Latin square design. Latin square design is also used a lot in animal science, for example. So here you have different animals. You have this type animal 1A, B, C, and D. And then you also have different period in which you want to give the drugs, for example. So here you control by the type of animal because you know the type of animal can affect the response. But you can also control for the week when you do the treatment. So this will give you what we call a Latin square design. So briefly, this is an overview of the experimental design. Now I want to shift a little bit and try how do I relate this to the models. Okay, so this is just a summary that if my experimental materials are homogeneous, then I can use completely randomized design. However, if my experimental materials are not homogeneous, then I can do blocking. That is, I can use randomized complete block design. If I have only one blocking, I block in one direction. If I have to block in two directions, then I will have a Latin square design. And then I can have a version of incomplete block design, can either be from the Latin square design or it can be from the randomized complete block design. So this is kind of a summary that can help you to make choices when you're trying to design your study, okay? So you can keep your questions. We can discuss at some point, but I promise you that we are planning to have a session for experimental design to have question and answer session. So all the kind of questions that you have, you're going to send them to us and we'll be able to answer them for you. So now let's look at the model that are related to these different designs. Okay. So the first thing that we have is that we looked at complete randomized design. We say in this case, the experimental units, the key thing is here. The experimental units are homogeneous, okay? So if there's any variation that we are going to observe between these experimental units that are homogeneous, then it should be because they receive different treatment. And anything else that we cannot explain now becomes the experimental error. Now, remember yesterday we talked about the pattern and the noise. So here you have, this is the pattern, this is the systematic pattern, and then the noise. So remember here we are saying that the experimental units are uniform. So it will not affect the treatment. It will not affect the responses. If it affects the responses, it will be uniform. Now, so only thing that will make the responses to differ will be the effect of the treatment. So that means in my model for CRD, I will have the effect of the treatment, and then anything else that I cannot explain, I will lump them together under our experimental error. So this is going to be a simple model with treatment and experimental error. Now, if the experimental units are not homogeneous, okay, then the first thing that we need to do is we need to group them so that we do what called randomized complete block design. So with randomized complete block design, the experimental units within the block, they're supposed to be uniform, but between the blocks, they're different. So here, when it comes to the sources of variation, you have the treatment effect, just like what we have in case of CRD. Then you have the block effect, and then we also have the experimental error or the residual, what remains. Then when we come to the Latin square design, so under here, our treatment is still there, but we also have the effect of the row. We also have the effect of the column, and then anything else that cannot explain becomes our model. So here you have two sources of variation. Here you have three sources of variation. Here you have 4 sources of variation. And that means the model, each model will have fewer parameters compared to the model of the Latin square design. Okay, so we talked about this. So here, this is for the CRD. So for CRD, this is the effect of the treatment. And then anything else that we cannot explain becomes our error. For the case of RCBD, you have the effect of the treatment. But because the experimental units are not uniform, you need to take care of that also in the model. And then anything else that you cannot explain becomes the error. And then for a Latin square, you have your treatment. And then there are 2 blocking factors. There is the column as a blocking factor, and then there's a row as a blocking factor. And then you have your error in that case. So this is how, so the first one here is the overall mean, that is the, okay. And then the effect of the treatment, is the one we put with this letter here, the effect of the treatment, the effect of the treatment. Then you have the effect of the block here. Then here you have the effect of the row, then the effect of the column, and then you have that. So these are, at least I wanted to show for you the relationship between the design of the study and the model. Now, if for some reasons some of these things are missing from the model, it's going to have an effect on the assumptions and on the many things that you're going to see later on. Okay. So let me see if there are some questions in the chat. Okay. So it's in a greenhouse where conditions are not homogeneous, or the strengths of different lights. Yes, you can use RCBD in a greenhouse, especially if there is direction differences in, let's say on one side is you have the sunlight coming from one end. So in that case, you can block using sunlight, or could be water, or could be reason. So that is possible. So you can use RCBD in a greenhouse. I'm doing my research and PhD entitled Climate Change, Perception, Adaptation Strategies, and the case of that. Please suggest the right model for this undertaking. Yeah, Taye, yesterday we had a discussion on how the model is supposed to be selected. So the first thing is you need to know exactly what is your response variable. So if you are talking about the perception of climate change, now how do you measure perception? Okay. How do you measure adaptation strategy? So a model's choice will depend on the kind of objective that you want to answer. So this, for your own, for this PhD of yours, you may have several variables that you're measuring, and each of the variable may have different model. So we cannot get one particular model that can solve all your problem. How do I state the hypothesis for more than 3 CRD scenarios? I indicated here that the hypothesis is mainly related to the treatment that you're trying to compare. Okay. Okay. So let me just end this, and then we go on ARA. Okay. So this is an example that we are going to look at today. So we're going to look at example of a randomized complete block design. But the twist is that there is what we call a covariate. So let me try to explain this. So we are interested in studying a relationship. Let's say fertilizer and effect of fertilizer on crop yield. Now, this is the relationship that we want to study. However, there are also some characteristics that can actually really try to bring us an issue here. So let's first go back to my favorite cartoon so that I can explain. Okay, so here we are interested in let's say the relationship between our treatments are energy drinks, and let's say ability to win. The response is your ability to win a wrestling match. Now, so of course, there should be a relationship between the energy drink and the winning, but that relationship can get distorted if you have different experimental materials. So these differences here is going to confound the effect that you have. One way of taking care of that is to do the blocking, as we talked about. But in some cases, you may not be able to do the blocking in all situations. So you still have to do something else in addition to the blocking. So here we have a small study here, which we just simulated the data. Okay. So here we have, this is the relationship we want to study. How does fertilizer affect crop yield? So we know that from theory that the higher the amount of fertilizer, probably the higher the yield of a crop, okay? But what about if there's differences in soil quality? Let's say, for example, this is my block 1. This is my plot 1. I have 20 kilos, I apply 20 kilos of say nitrogen here. Okay. And then this is my block number 2. Let's say I apply 60 kilogram here. Okay. Now, let's say in this case here, that this soil here, the plot here is more fertile compared to that. So you can see now that as much as I'm going to make comparison between these two, I need to take into consideration the fact that I have different soil fertility. It could also happen that you set up an experiment. Let's say you set up an experiment in the field, and then in the process of running your experiment, let's say something comes and damages part of your experiment, like here. So here we have some damage. Let's say maybe the goats comes and eats part of your experiment. Okay. So what we could do in this case would be, we could assess the damage. So let's say these are different plots. Let me say we have different plots. So you can see some plots are not affected. So if we score, let's score damage. So this, if we are scoring a damage on a plot on a scale of 1 to 10, this plot has no damage, so it could have a score of 0. This one have no damage, a score of 0, a score of 0, a score of 0. But this could have a score of 8. This could have a score of 7. This could have the upper one, the lower one could have a score of 5. The upper one could have a score of 7, and so on. So this is now the information that you need to use as a covariate. This is what we call a covariate. So a covariate is also part of the variability, but it cannot be used for blocking. So something can come up when the experiment is already going on and then can cause a bit of a problem. Or let's say, for example, you're doing experiments on nutrition. You want to see the effect of a certain diet on weight gain. Now, if you're going to start an experiment with 2 people, one weighs 50 kilogram, one weighs 60 kilogram. If you cannot use that information for blocking, you can use that information as part of covariate. So with the covariate analysis, then would mean that we are going to correct for the covariate. So a covariate is simply a variable that is measured and included in the model alongside the main predictors to account for the influence on the dependent variable. So here we have an experiment where we have 5 blocks. That is randomized complete block design. We have 4 different treatments, and then the response of interest in this case is our crop yield. But we realized that before we applied our treatment, the different plots have different initial biomass. So we need to take that into consideration, because if you have a plot with high biomass, the response of that plot is likely to be different from a plot with a low initial biomass. So we can have two models. You can have a model where you have the treatment effect, you have the block effect, but you don't control for the initial mass. Then you can have this where you bring this last part here. Now, this first one is our analysis of variance that we all know about, ANOVA. And then this one is what we call analysis of covariance. So we are going to add a covariance into our model. So it's called ANOVA. So what I want to try to illustrate using this example is that if you don't specify your model fully, you are likely to have a lot of violations of our samples, and you're going to end up with model with results that are actually not valid enough. So this is going to be what we are going to do. So maybe we can, I want us to switch a bit to ARA now, so that we are able to see. So let me see, answer a few questions. How do we determine the number of blocks? So the number of blocks for randomized complete block design is related to the number of treatment. So it's also the same question, how do we determine the number of treatment? So it depends on many things, including the resources that is available to you. It depends on how much variability is there in your experimental material. It depends on what kind of differences do you want to detect. So I'm going to have that. Rawia, the material will be shared. The link is shared. I think my colleague has shared the link. Access, the links is shared. I think we have answered most of this. Let me check the chat and we see if there are some questions in the chat. Day one will be captured by Zoom. Okay, let's have a 5 minutes break, but within this 5-minute break, what I want is that I want you to download the information that was shared today, and then we are going to work on that. We're going to run I don't know how my colleague shared it, but it should be day 2. And in that folder, you have will have the data that we are going to analyze. You'll also have the R script that we are going to use for the analysis. You're going to also, this presentation is also present in that particular thing. So while we wait for the break, so let's say we are going to start at, let's say we're going to start at 3:20. So that is, you have about 11 minutes. So can I also ask those who have not installed ARA or ARA Studio to do so? Okay. So we have a little bit of a break. Within this break, we can have some discussions. The drive will be shared. Yes, Gerard, you have your hands up again, or that's the all hand? Yes, Gonzalez. You can unmute Gonzalez, and then we hear a bit.
Abba or Gonzalez, please unmute and ask your question.
Yeah, you need to install both ARA and ARA Studio. So Samakula, install ARA Studio as well. We are using the same link. The information just get updated. We update the same link. So if you have the link of yesterday, you can use the same link. Say, I want to compare aflatoxin in groundnut in a certain regions. What model can I use? Yeah, so I think if you look at the presentation that I gave yesterday, we looked at how do we select the model. So if you have aflatoxin as the response variable, what are your explanatory variable? What are your predictors? Do you want to compare regions? Do you want to compare maybe the rainfall in the different regions? What do you want exactly? That will determine the model that you have. So you first need to be able to identify the response variable, identify the predictors or the explanatory variable, and then you need to look at what kind of relationship do we have in that. So what's the difference between ANOVA and ANACOVA? I said ANOVA is when you deal, or in both cases, the response variable is continuous. In the case of analysis of variance, you only have the treatment that are mainly categorical in nature. In addition to the treatment in the analysis of variance, in ANACOVA, you have an additional covariate that the covariate is also quantitative in nature. So you use the covariate to correct so that any confounding as an effect of that. We are going to see the results. Yes, Gentile. I say I've just updated the link, but no added material. I think my colleagues should have added the material. Ellen, have you been able to do the update? Anybody who has succeeded in getting the new material for today? Can I see in the link? Yes, there are people who have done so. Yeah, so we can we need to be able to. Yeah, I think a lot of people, apart from a few, could we get shared with the app for ARA? The ARA is downloaded directly from the internet. You don't need to have shared. I mean, you can go to Google and you go and just type install ARA and then you follow the link. Somebody said I'm not understood I'm going to, when we go to do the analysis, you're going to understand. So the link is being shared again. Please, the form, there's also a form that if you already filled the form, you don't need to fill it again. So check the forms have been, the link has been shared again in the chat. Stephen is asking, can multinomial logit model? And the question is not complete. Yeah, at least the view. So the file that I shared is a CSV. It looks like you can open in Excel, but it's a CSV file. Okay, so let me try to look through what was shared. and then we can start. So I'm going to stop sharing this. Somebody still asking, where do we get the file? I think a Google link has been shared. Please look at the chat. WhatsApp group has not been created. If you want to create a WhatsApp group for this training, that's fine. You can go ahead and do that and you share. Yes, the drive is being shared. Please download and look at the material for the 2 days. You say we can use the same group for bioinformatics. I don't know. You can decide. Yes, the last question. Joshua, you have a question? Okay, so I'm going to stop sharing this and then
on the WhatsApp group, we've been having quite several WhatsApp groups. We already have one WhatsApp group where Dr. Dong and the team are, and I've posted the link in the chat, but we don't have so many other WhatsApp groups.
Okay, good.
But they are programming Reform 2023.
Yes, I think they're...
And I see many of you are joining already. Please let us just repeat that we shall not be sending out recordings. The recordings are available on YouTube. The session is streaming live on YouTube. So if you want to catch up, please go on our YouTube channel and catch up with yesterday's recordings.
Okay. So the recordings are on YouTube. Please look for Forum YouTube channel. Even the previous training that we had are all there. There are lots of material there that you can always find. So I want us to open those who already have. I'm just trying to confirm that you have a file called data2 script. Okay. Data2 script. Are you seeing my screen? Okay. And then, so that is that is our script. So as my colleague introduced this yesterday, in our these days, the most important thing is to have your script. And once you have a script, you can always modify a script. You can get somebody's script and modify and use it for your own data analysis. So the script that we are going to share with you, you can utilize it anytime you want to do a similar analysis like what we are going to do today. And then in the same folder, you need to have there's a file which is rcbd_with_covariate.csv. So that is the data that we have. So that's our data set, which we are going to analyze. Okay. So is that clear to everybody? So I want you to have that folder where you can access it, because we are going to make that folder what yesterday my colleague talked about as a working directory. So I think we can now start. So I'm going to open, okay? What you can do is there are many ways you can open an R script. So the best thing we can do is we can just, if you have the script here, you can right click and you open with RStudio. Okay. How many people have succeeded in opening the script, the data2 script? How many people have succeeded? Can I see in the chat? Yes, yes, yes. Okay. Okay, so I think a number of you have already opened it. So as you can see, we have, let me try to first increase the view a little bit. Okay. So as my colleague yesterday indicated, so here we have the window. The upper window is where you can type your R script. You can type your R command. And then below here where I'm trying to highlight, that is our R. Now, it doesn't matter. Yours probably could have changed shift position, but it doesn't really matter. So you can see here, this is, in this case, tells me that R version 4.4.3, that is February to February 2025. So here is my R. So we can clean the content here. Now there is something that looks like a broom. If you look on top here, on top of the R here, there's something that looks like a broom. If you see the cursor that I have here, if you click on this, that looks like a broom, it clean up the console. Okay, so we have four different windows. This is the window where your command is. This is your R console, the one below it. And then the one on the side, there is an environment, which in our case, you can see mine is written empty environment. And below here, we have where you can see your plots and other things. Say yes, a lot of packages not to install. Yes, we are going to install the packages. Okay, so the first thing that we need to do is we need to install the packages if we have not yet done it before. So what is a package? I think my colleague talked about the package yesterday. Packages are sets of functions that you can use to do analysis. So for example, here we have EM means. So EM means here, this is used for giving us, calculating for us the means of the different treatments. So if you want to install this particular command, this particular function, this particular library, we call it more kind of library, but it's a package, then we use this command here, install.packages. Okay, then you open the bracket and the package name should be in a double quote. So here I mean I am going to install this package here. Okay, the next one is another package which we call tidyverse, and then there's another package which we call agricole, and then there's a package which we call ggplot2. Now, when you're installing the package, you need the internet. But once you already installed the package, you don't need the internet, so you can use ARA offline. When you see here, if you have this sign here, anything that appears after this sign here will be green. Now, with this sign here, you're telling ARA that whatever is going to appear after this sign here is just going to be your comment so that you can read later and understand. So ARA does not run this as a command. So if I put here, I put this and I say installing package agricole. So this one here is just to remind you that this is what this command is doing. And then I can see right here, installing package ggplot2. Okay. So after this, that thing will be done. Now, I'm going to request you to run line number 2, number 3, number 4, and number 5. If you don't have them, if you have not yet installed them. So if you've already installed them, then you don't need to run these lines. So how do I check if the package is already installed? So what you can do is, for example, to know whether this package is installed, this EM or EM means, what I need to do is you run the library, you run this line here. If you run this line here, like in my case here, if I run this line here, if it doesn't tell you there's an error, that means you already have the package. So for number 1, you try to run this line. Try to run this line. If you get something that looks like mine, that means you're okay. You can also run line for tidyverse. Okay, you see what it displays for you. This is double. Okay, so the first thing is before you can use a package, you need to install it. So the second 4 lines, these are all installing these different packages. So the first thing is you need to install the package. Once you've installed the package, then you need to call that package to start working, to start using it. So it's not enough to just install. Every time you want to run, you can now call the package. So if I want to run this library, I call it, I call the other one, I call the other one, I call the other one. So let me go to the chat. How many people? Okay, somebody say install package. Oh, if he said connection cannot be found. If connection cannot be found, probably means you don't have the internet. Kauma Samuel, install the package, connection, that means you don't have the internet. You need the internet to do the installation. Okay. What do we mean agricole package? Agricole is one of the packages that is used for used for doing a lot of agriculture-related experiments. So it was developed by a master student from Colombia or Chile. If you get an error, what kind of error did you get? Okay, you can post the error that you've got in the chat, and then my colleagues will be able to probably tell you what could be the problem. So how many people have installed the first package? Okay, I can see a number of them. Okay, can those ones who have not installed post their error in? We want to see the error. No. Don't run please don't run, don't go. We are not yet there. So please, I only want you to run what is up here. Somebody is saying, trying to run a directory. Okay, so I can assume that okay, so Francis, you're saying error, there is no package called Agricole. So what you do, you go and run line number 4. So that shows that you have not installed the package. So you need to first install the package before you can run the Agricole package. Yeah, if your connection is poor, then you're certainly going to have a bit of problem doing that. Okay, so Kibande, you're okay? That is fine. That shows that you have it. That's not an error. So the issue of error tools probably means that it could be related to the computer that is using. So package Agricole was built under 4.4. That's fine. So please install tidyverse, install Agricole, install ggplot. I want to install the 4 packages there before we can go and run. So somebody can you post the the link? Error tool is required to build the packages, but is currently not installed. So you can try to install error tools. You can go to Google and say install error tools. James, you have a bit of problem with I think it's a bit of setting issues. So James, what you need to do is you need to first install the package. When they say there's no package, mean you first need to install the package. So what is error tool used for? Error tools is used for compiling some cases. So it's a bit of it could be related to your computer system. In most cases, most people don't need any error tools. You first need to install the package before you run. You first run this. If you successfully run the second line from line 2 to line 5, then you can run line 6 to line 9. Before that, you cannot proceed. Please try to post most of the thing on the Q&A session. Q&A. Okay, anybody want to show their screen? If you have a bit of problem, you raise your hand. We ask you to share your screen. So you are the one showing Tinyverse was built under this. That's okay. I think that is fine. So please install all of them: the eMeans, the Tidyverse, the Agricole, and the ggplot. So you can never use a package unless you install it on your computer. And for you to install it on the computer, you need to have an internet. But once you already have it on your computer, then you will not need the internet anymore. But for any new program for any new package that you have not yet installed before, you need to install using the internet. So the best thing will always be to try to get as many packages as possible install on your computer, the one that you're likely to use, then so that next time you want to use, you'll have that. Okay. So I'm going to give you let's say another 2 minutes. We wait for everybody to do the installation, then we move to the next step. I need somebody to first share the screen. Who wants to share the screen? Who is having a bit of problem? And then you try to share the screen and we see. There are a number of other tools issues. Okay, Eric, can you share your screen and we see? Can you allow Eric Katamba to share the screen? So you allow Eric Katamba to share the screen. I can I can stop sharing mine.
Eric, please go ahead and share.
I'm not yet able to share the screen.
What's appearing on your side when you start sharing, when you look for sharing?
It is not yet appearing yet.
You've seen the share sign?
No, it is not appearing on my end.
You're not seeing the green thing with the arrow?
Can you check it now?
It is not.
Please check it now.
It is telling me to join as a panelist. Should I?
Please
you
click
join.
yes, join so that you're able to click it. Okay.
Okay, so you can share and we see. So you will see that once we do the preliminaries, you know how to install, you know how to call. The rest will become a little bit more routine sort of stuff.
Okay, and now let me share. I don't know if you can see my screen now.
It's starting to, okay.
Yes, now the biggest problem is here. It shows that it says that there is a binary.
No, but if you run the library, if you try to run line number 10 and we see.
Okay.
Thomas.
So you're
Dr.
okay? Yes, Helen.
I think that for those that are getting the challenge with the R2s, whereby it is failing other packages to load, they need to go on internet and say, like, install R2s, and then they follow the procedures because it is very easy there. In case they can't do it, then I can show them how to do it. Thank you.
Okay. Yeah, so you need to go on the internet and install. I think, Eric, you don't have a problem. If you can run line 6 up to 11, up to 10 without any issue, then you're okay.
Oh,
no,
okay.
the red things are okay. The red things are okay. When it tells you there's error is the red one is a warning. That's fine.
Okay. Thank you.
Yeah, so you're okay. Yeah, you can stop sharing. Any other person, Phillips? So, Selma, can you allow Philip to share? Or one of the guys,
Okay.
there are 3 people.
Philip,
Then they see Damilola.
Philip has been promoted.
Okay.
You can go ahead.
Okay. Hey, first go up. Okay. Go and we see the. But can you run line 6? Okay. Can you run line 7? Can you run line number 3 and we see what is happening? What's going to happen? Line number 3. So let's wait. Could it be the weak internet? Okay, you continue. Let it run. Continue running. So once you still see the red, what is it? This red polygon or whatever, the many-sided, that means it's still running. So you have to wait until it is finished. But it looks like it's more to do with the internet than the. You have to be patient. If you're not patient, then you see. So maybe the issue of the internet. Cannot open compress. Go up a little bit and we see. Yeah, I see timeout, and I think it's more to do with the internet. Yours is more of the internet. Can you try number 8, line number 8? I think it's more to do with the internet. Yeah, so I think it's so the thing is, once you, yes, please.
Dr. Thomas, he did not install, and that's why there's no package called this. He has to first run 2 up to 5. When those packages are installed, that's when the libraries will be able to run.
Okay. No, I was just trying to tell him to run that to check whether I think the internet is a problem.
Even the internet
it seems not.
well. It seems
okay. So you can stop sharing. You need to improve your connectivity. But once you have a good internet, you should be able to run. The first thing is you run 2 up to 5, and then you run that. So let Rawia show us the last one. There's another so can we promote Rawia, then the Milola, and then we can move. Okay, so somebody said, can you explain why the packages need to be libraried? Okay, the first thing is that once you have your package installed on your computer, for you to run the package, what you need to do is you need to call every time you open a session you want to run, you need to call it. Calling it means you're bringing it in the environment so that you're able to use it. If you don't do that, then it will not be available for use. What is the use of other tools? Other tools can help you to it helps with the compilation and getting the programs to work, to get installed. Okay, so I think we can proceed. So let me go back to my share my R Studio again. Okay. So the first, so for a new program that you've not used before, unless that program comes with the base R. So there are programs that comes automatically with R. Once you install R, the program will already be there. But in most cases, for new program, you need to install them. So after installing them, then you need to run the library. So we can run 6 to 9. Okay. So then the next thing that I'm going to do is I'm going to explain the issue of the working directory. Now, if you want to call a file, there are 2 ways, there are different ways you can do. Now, the best thing for us to do is, if we know where the file is, then it's better to set where the file is as a working directory, so that when you're going to read that file, ARA will look for it within that that folder. So the thing here is then that I need to know. Okay, the first thing is, this is my advice to you. So before you do any data analysis, you need to prepare a folder where you're going to have everything concerning that particular analysis or that project in. So the first thing that we're going to do is we're going to create a folder, and in that folder, you're going to put any data that you want to analyze that be dealing with that in that project. You're also going to save your results in that folder. You're also going to put your R script in that particular folder. So it's a good working ethics that you know where the work is going to be done. It works like if you are in a room. So when you are in a room, you're working from. I mean, let's say you're working in your kitchen. You don't keep your knife in the bedroom, because every time you want to look for a knife, you have to run to the bedroom and pick it. So the same thing here is that I create a folder where I put everything that I need. Like if you want to cook, you go to the kitchen. In the kitchen, you have everything that you need for cooking. You have the water, you have the plates, you have everything there. So this is also what we need to do. We create a folder. In that folder, we put everything in, and then we tell Ara, please, let's go to the kitchen, and we work from there. So this is the process of specifying how you're going to specify the path. So what you're going to do is you're going to go to, if you go on top here, do you see where it's written session? Where you see where it is written session, you go there, session. You go to set working directory, and you go to choose a directory. Just see what I have there. So the first thing is on top, you have where it is session. Under session, you go to set working directory, you go to choose a directory. So this is where you're telling R that for this particular analysis, everything that we are going to look for is going to be in this particular directory. If you're good at program, you're good at computer, you may not need to set a working directory, but it's just good manners to have a working directory where you keep everything in. So the first thing we need to do is we need to set a working directory. So if I come here and I say choose a working directory, then I need to go and look for. So mine, for example, I need to go to my document. Under my document, I go to trainings. I go to trainings. Under training, I have Forum. And under this, I have, now there's a folder I call day 2. So this day 2 is actually the folder that I want to make my working directory. So what I need to do is I need to tap on that. Okay. Don't open it. Just tap on it like that. Don't double click on it. Just tap on it like that. And then you click on the open from down. There's the word open from down. When you click on that, then it will give you this statement here. Okay. For mine is, remember mine was, I went to the document. From the document, I went to the training. From the training, I went to Forum September 2022. And inside there, I got a folder I call day 2. If you click under day 2, you may not get anything. So here then, the command is here. This is the command that you've actually done. So you can see mine is here. The same command, I can run it there. Okay, how many people have succeeded in setting a working directory? Somebody said didn't see the process. I'm going to repeat it again. Okay, so let me repeat it for the sake of other people. Yes, Damilola? Do you want to share the screen? No, Zanele, don't run that command, because that command is for what is on my computer, not on your computer. So you need to look for where yours is. Yes, Damilola, can you Do you want to share, or your hands is up? Can you allow Peter Amoa to share? And we want to see so that he can demonstrate for us how to get set a working directory. If one of you can share, then that would actually make life a lot easier.
Who should I allow to share? Peter or
there's Dami. What's that?
Damilola?
First, make Damilola share first, and then Peter can share. Janelle, you don't need to go further than okay, so let one of the persons share first, and then we can proceed from there. Maybe it's easier because mine, you said, is hidden. So if somebody else can share.
Doctor, you are still sharing.
There?
You are still sharing the screen.
Oh, let me stop sharing. Sorry.
Okay, I just stopped it. Okay.
Yeah, that's fine. Yes, Robert, what you need to do is you create a folder, then you pick the files, the files that fold the two file, and you put it in.
Please, if you are asked to share, we promote you to being a panelist. So you need to join. You click the pop-up that will come on your screen for you to join as a panelist. If you don't click on it, then you will not be able to join.
Then you'll not, yes.
And share. Damilola, please accept the invitation.
Egata, please don't run my line, because the line that I have there is the folder on my computer, not on your computer, so it's not going to work. So is Damilola going to share or not, or you promote another person?
Let's promote another person. Please raise your hand if you are ready to share.
Even somebody who has done it already well. If you've done it well, okay.
is finally in. He can share.
So you can share your screen. No, we are going to repeat. We wanted one of you to do that so that we can see. So we're going to repeat. Damilola, what is happening? You're not sharing?
Please, can someone else raise their hand so that we promote them? Who is willing to share? Judith, you are promoted.
You can try, Judith. Okay, Damilola is sharing. What happened? Okay, Judith, can you share? Okay. Okay, Judith, do you see on top there you have there are two kind of there are like two squares, one on top of each other. You see on top of your R studio, on top of your R, you see where there's R 4.1.1. Can you go on the other side and you see on top? No, move. Okay, you see on no a bit on back on above the console. Do you see any two? Do you see any two squares? No, not there. Come down a bit. The lower part. Move the other side. Move to your left. Okay, that one. Click on that. No, click on again. Okay. So you see now what you have is yours is just on a different side. So here you have your script. Can you go up on the no click on the R data 2 R script. Click on that. Okay. Can you go up? No, on the same one, you can scroll up to line number 1. Okay. So what I want you to first do is you show how you got to how you did the setting, the working directory. Can you demonstrate how you did the setting of the working directory for your colleagues to see?
Okay, how can I okay.
No, it's okay. We are seeing it there. So can you go to the session?
Like for imins?
No. Yeah. What we wanted, first of all, is how to set a working directory.
You go to session.
So you guys follow, can you follow?
Then set working directory. Then you choose the working directory.
Okay.
Then mine is on training forum. Then I open.
Yes.
Like that. That is it.
Okay. So you can copy that statement there and replace with mine. You see mine there, the line number 12.
Number 12, yes.
Can you copy yours and replace with that one of mine? Remove mine.
Okay. So I copy mine. And then.
No, without the last part.
Okay. So up to S.
Yeah, up to there.
Okay, copy. Then I
and then replace with mine there.
So how can you replace? Wow.
Just paste it on top of it.
Okay.
Okay.
Like that?
So that means next time you want to run, you just run that line and you go to that directory.
Okay.
Yeah. So now, yeah, that is okay. But did you have any problem with the installation?
No.
Okay. So I think I think she has made it very clear. You go to session, go to session, choose a directory. Okay. Do it again.
Yes. Set working session, set working directory, choose directory.
Choose a directory.
Then you find the folder. Yeah.
Okay, good. Thank you.
Thank you.
So anybody with the challenges of setting a directory? I want now anybody with challenges setting a directory to raise their hand up, and then we can do that. Then we should be able to proceed to do the analysis. Yes, Peace. Are you having a problem? Okay, can you promote Peace?
I'm not seeing the hand for Peace. Can
Okay,
Peace raise a hand? I'm seeing
there's
Isaac
Isaac Tamba. You can maybe promote Isaac. I want somebody who has failed to set the directory.
Isaac, please join as a panelist. Leviticus, please join.
Okay, okay, you join, then you. So how many people still don't have how many people are failing to set a working directory? I can assume now that we've set the working directory.
Yeah, some people are raising their hands, but they are declining to share. So that's
okay. Maybe Dembure. We are giving opportunity to one person, then we proceed. Okay, I can see sorted and okay. So the what you need to do in this case is okay. I'm going to share my screen. Yeah, but you guys get promoted, but you don't want to share. Do you want to share the?
They are all declining to join us, to be promoted to being a panelist.
You first need to accept to be promoted to be a panelist before you can share. So if you don't, then if you click no, then that will be. You pick one of them for another try, and then we call it off.
Okay. Okay, I'm promoting David Kabanga.
Okay.
Please click on the link on the prompt on your screen. Also, Peter Amoa. Please also check the pop-up. Okay, Peter Amoa has accepted and is joining. Peter, you can go ahead and share your screen.
Okay.
Can you share the screen? We are seeing you only, the face.
Okay. Okay. Yeah, I think I don't know if you can see my screen.
Okay,
now.
yes. Okay.
Okay, so in setting up the working directorate, first of all, I think doctor said you go to the session aspect. I don't know if you can see, all of you can see my cursor. You go to
yes, we can see.
Okay, you go to the session aspect, then you locate the set working directorate, then finally you choose the choose directory. Then it will take this dialog box will open. Then I'll go to where my
first start with the desktop. Okay. Then you look for the desktop on top on the desktop.
Okay. Yeah, my files are stored inside this particular folder. Then I'll click on open.
Okay.
Then after I'll copy this set working directorate. I'll paste it here. Paste it here. Then I'll click on run.
Yeah, but what I was trying to do that if you have it there, then next time you don't need to go through the session. You can just run that line and you get to the working directory.
Okay. Okay, sir.
Okay, so I think this one should be clear to everybody. Okay, so now I can come back. I go to my... Okay. So if we have reached this point, so the next thing is, in this case now we need to import the data. So line 13 here is, okay, so why are we using, we are using, this is the function that we are using to import the data. And as you see from here is written read.csv, okay? So what are we reading? So this is the function that calls the data. Then this is the name of the data that we want to read. And you can see it ends with .csv. That is comma separated values. So if you run this line, what you're going to do, you're going to go inside your folder. You're going to pick this data set here, and you're going to create an object which we call a df. So that is going to be the name, the object that you're going to create. So we can run this line number 13. So from here, you can see that under the environment, you have your df. Df here is just a data frame. So you can use any name here. Any name you want, you can use it there. So this one shows us that we have 20 observations for variables. Okay. You cannot have more than one variable in a more than one folder in a path. Okay. So how many people have succeeded in, can I see ones, those who are called the data? Okay. Good. So now we are going to, okay, good. So the first thing is that once you have your data in, you need to start doing some inspection of the data. So line number 16 has a function names, and this function here is going to give us the name of the variables in your data set, which is we call df here. So if you run this line here, it will tell you that the first variable is called block. The second variable is called treatment. The third variable is called initial mass and biomass. And then the fourth variable is called yield. Okay. So that won't tell you the names of the columns. The next one is DMI, dimension. So dimension here will tell you how many rows and how many columns. So if you run your line number 17, you should be able to get 20 and 4. So mean you have 20 rows and 4 columns. You can check the first 6 rows. So if you look this command here called head, so the head will give you the head of the data. If you put tail, it will give you the tail of the data. So if we run this, you see now it gives you block 1, 1, 1. In block 1, we have treatment A, we have treatment B, treatment C, and treatment D. This is the biomass, initial biomass. This is the initial biomass, and this is the final yield. Okay? So you have a rough idea what is going on in your in the data set here. Okay, are we together? I know tomorrow we're going to run a bit faster, but for now, I think. Okay. So the next thing that we are going to do is we are going to look at the structure of the data set. Remember, we indicated yesterday that the type of variables that you have can determine the choice of the model. So let's run 19 and then I explain to you what it is. So if you look at the structure here of the data, now it will tell you that this is a data frame. I think yesterday my colleague talked about a data frame, and it tells you that we have 20 observations on 4 variables. Okay, the first variable is called block, and this one tells you that accordingly they're integers. You have 1, 1, 1, 2, 2, 2, 2, 2, 2. And then the second variable is called treatment, and this one tells you that they are characters, the CHR. So you have A, you have B, you have C, you have D. And then the initial biomass, it tells you that this is numeric, MNUM. These are the values that we have. And then the yield is numeric, and these are the values that you have. Now, we know that the block and the treatment are categorical, in that you either belong to block 1 or block 2 or block 3. You either have treatment 1, treatment A, treatment B, or treatment C. So what we are going to do is all the categorical variable, in this case, we are going to convert them to what we call factors. And so this is what we're saying, that we're going to convert categorical variable into factors. So what we're going to do here is we are going to go into our data set. Our data set, remember, we call it DF. And the $sign is used to select a variable that you want to work on. So you go inside here, select a block, and then convert it into a factor. Once you convert it to a factor, you put it back into the data set with the same name. You would go and do the same thing. Go into your data set, pick treatment, convert it into a factor, and put it back into your data set. Okay? So once we run this line here, line number 21 and line number 22, we do then check the structure to see whether there's any changes in the structure of our data. So we can run our line number 21. We run line number 22. Now, if we now look at the structure of the data again, remember initially we look at the structure, it told us that it was a data frame. The first was a block and it was an integer. The second was treatment, it was character. And then the last two were numeric. So we are going to change these two. They should change from integer and character into factor. So let's check. Okay, so you can see from here now that, okay, so you can see this is still a data frame, 20 observation, 4 variables. The first one is a block. Now you can see now it is a factor with 5 different levels. So remember in this case, in this example, we said we had 5 blocks. So there are 5 levels. So block 1, block 2, block 3, block 4, and block 5. And then the second is treatment. Is also, this time we have also converted it into factor with 4 levels: treatment A, treatment B, treatment C, and treatment D. And then you have the initial biomass, which is numeric. We left it the way it is. And then we have the yield, which is numeric. We also left it the way it is. Okay? Can you explain more line 20? Okay, so let me check line 20. No, okay, so what we are trying to do here is just, this is an instruction. This is what we are saying, that what we want to do in this case is that we want to convert block and treatment into what we call factors. So factors are categorical in nature. So in this case, the block, which is part of the design, and the treatment, which is also part of our, are the ones that we convert into factors. And these are the ones that we are going to use in part of our analysis. So this is not a command, this is just a statement. And remember, we started it with this sign here. So when I put this sign here, it just becomes a statement. So the actual action is here. We are converting a block into factor. We are converting a treatment into factor, and then we check what it is there. You got lost from where we are getting the data file from. Mr. Olet, now I don't know. Did you get the folder that was shared? The link was shared, and in the link we have all the information that we are trying to analyze now. Okay. Let me check in Q&A if there are issues that. So the $sign is used to select a variable from a data set. That is what you need to do. How do I delete a variable? You don't need to delete a variable at this point, okay? Okay, so the next thing that we want to do now is we want to look at our data set, and we want to do some exploratory data analysis. So we can use this simple command called aggregate. Aggregate means I get my yield, which is the variable of interest to me, and then I divide them up into different treatments. So I have yield for treatment 1, A, treatment B, treatment C. This is my data set. And then what do I want? I want a summary. So what will happen in this case, that if I run line number 26, so you can see from here that it got for me treatment A and gave me a summary. The minimum yield in A was 24.8. The first quartile, the median, the mean, the third quartile, and the maximum yield. Okay. I can do the same thing here, but this time I only want to get the mean. So the first part is the same. It is yield. I aggregate it by treatment. This is the name of the data set in which the two variables are coming from, and this is what I want. I want the mean. So if I run this, instead of giving me all the other numbers, it will only give me the mean. So you can have the mean for A, the mean for B, the mean for C, and the mean for D. Here we summarize with treatment. We could also summarize yield with block. We want to see how the blocks are performing in terms of yield. So here you have your yield, which is the response variable. Then you have this small sign here. It's called tilde. And then this is the block. And in this case, we get the summary. So you can see from here, block 1, this is the information from block 1. Block 2, this is the information from block 2, block 3. So based on the mean, which is the highest yielding block here. Based on the mean, which is the highest yielding block here. Can you type on the chart? Which is okay, people are saying block 3, 3, 3, 3. Okay, it's true, it is block 3. Okay, good. So you can see here block 3. You can see the minimum yield in block 3 is 32.6. The first quartile is 39.78. The median is 42. It has the highest median. It has the highest mean. It also has the highest third quartile, and then it has the highest, not the highest maximum. The highest maximum is in number 5. So you can also just look at the mean alone, and then we can have that. Why not 5? Because I said based on the mean. Which one has the highest mean? Let me see, maybe 5 has the highest mean, but the highest mean is 40, which is from 3. Even the median, the highest median is 42. Okay, let me check if there is any question in the Q&A that needs my attention. In line 27, can we have the mean, the standard error, and that? You can try it out. You can change. Let me see if we put here. We say we want the mean. Let's say this. We can run that and see. It doesn't give you that. But you can play around with that. That is possible. If you want the standard error, you call FDSD. You can run. It gives you that. If you want the variance, then you can have it as VAR. You can run it and you'll get that. Okay. So, this is when you're using just numbers to do the description. So the function aggregate means, in this case, what we are doing is we are getting our response variable, and then we are going to group them based on on treatment in this particular case. And once we group them based on the treatment, then we do a summary for each individual treatment. That is what aggregate really means. We can also do you can also do the box plot. So the box plot is presenting the information in we can present the same information but graphically now. So we can have this. Okay, so you can see from here, I started with line number 34, but it could have started, we can start with line 31. Okay, so here you can see the box plot for treatment A. Then you see the box plot for treatment B. You see the box plot for treatment C, and then the box plot for treatment D. The thick line in the middle is the median. Below here is the lower, the minimum. Up here is the maximum. Then you have the first quartile, and then you have the third quartile, and the median is in the center. You can also do it for block. So you can see here, remember we're talking about block 3. So you can see block 3 with the highest median. And then we have 5 as the highest maximum. Yes, somebody was raising the hand up. No, I said we'd aggregate. So Lucas is saying that the box plot, you have the figures have a margin. So a wide margin means what you can do in this case is you can play around with your margin like what I was doing there. So probably yours is a bit squeezed like that. That's why it is not giving you the thing. So once you have a sizable, it should be able to run. I think I have explained the aggregate well now. So Masiko, Lucas, you should be able to run that. You just adjust the windows for the graph and make it bigger. Then the rest should be okay. The box plot is used to summarize the data. What it does, it shows you the minimum observation, the maximum observation. It shows you the median. It shows you the lower quartile. It shows you the upper quartile. Okay. Could you please share the link to access the script, please? This thing was shared, I don't know. If you are, I mean, the same script of yesterday, the same link of yesterday. Okay, my colleague has shared it. Yeah, the link has been shared. Okay, so the box plot literally shows for us the variation in each category. So here you have for block 1, block 2, block 3, block 4, and block number 5. What about the outliers? Yes, the outliers, in this case, if I run for you the one for the treatment, when you see a point that is alone, that is an outlier. So we can see that in D, treatment D as an outlier. An outlier is an observation that seems to behave differently from the rest. Okay, so we have looked at the box plot for the biomass and the box plot for the yield. Now, so what is happening here is that what is happening here is that you have yield of a crop, which is your main response variable, but you are told that before the experiment was started, the plot already had some plans, and those plans had different plots at different biomass. Now, because they have different biomass as a starting point, that would also affect the ultimate yield that you're going to measure. So what we need to do in this case is that we need to take into consideration the biomass if we are going to do the analysis. Otherwise, we are going to have a bit of problem with the analysis itself. Somebody trying to raise their hand up. Now, Kirunda said we have downloaded the file. The folders are not empty. There must be something in the folders. Otherwise, the people will not be running this thing here. So we need to see exactly what could be the problem. Okay. We can also do a box plot using another. We can do plots using the function ggplot. Now, the function ggplot comes from the package ggplot2. Now, this one is a very good package for drawing graphs. And it draws a lot more. The graphs are more elegant, and you have a lot of flexibility that you can do. So the thing that we are trying to do here is, the first thing is whatever you want to draw, the name of the graph that you want to draw comes after. It always starts with geom and then a dash, then the name. So geom box plot means you're going to draw a box plot. So let me try to explain this a little bit. So we have the first part here. So with the first part here is, this is the function ggplot. This is the data set, the name of the data set. And then in here, we have what called aesthetic. So here, I have what I want to have on the x-axis, and here I want have what I want to have on the y-axis. So what literally you're doing here is you're drawing a blank slate. So I can run this part only. So you can see now with this, I have yield treatment on this, and then I have yield on that. So you can see there is nothing in the graph. It's just a blank slate. Now the drawing is going to come. You see this plus here. Mean on top of this, I'm going to add box plot. So the first part is blank, and then after you've drawn your x and y, then you're going to add a box plot. So if we run this, so you can see now we have the box plot inside, the same box plot like what we had before, but this time it has a different design in the background. Okay. Now we can still continue to modify more and more. The other thing also, what we could do is this part remain the same, but we change a little bit. We're saying we want the treatment to be on the x-axis. We want the yield to be on the y-axis, but we want to color using the treatment. So we want different treatment to have different colors. So that is the first part. If you run this, it gives you a blank. Then the next thing is if you add this on top, you add this, and after adding that, then we can do another thing. So let's first run from here up to here. Okay, so you can see here, we have for treatment A, treatment B, treatment C, and treatment D. So here you have your box plot. The color is now, for A is red, then green, then purple, this is a blue or light blue or something. Okay. The next step would be I can add something else. So here I want to add for each of these, I want to do for each block separately. And then the last part here is going to add the title. So if I run the whole thing here, so now it gives you a box plot facet by block. So you can see from here, okay? So this is, you can see here, this is treatment A, B, C, D, A, B, C, D, A, B, C, D. So you can see where there's red, that is our treatment A. So if you look at block 1, treatment A at the lowest value. When you look at block 2, treatment A still at the lower value, but is the same value with the treatment B. Now, when you go to block number 3, now treatment A has the highest value. When you go to 4, it has the lowest. When it goes to go to 5, it had the second. So there's something happening. The performance of our treatment A seems to change with the block. And this could be related to the characteristics of the plants in the different blocks. Remember here we're talking about having the initial biomass already there. With the initial biomass already there, that means you're building onto something that you already have. So now let's look at the biomass itself and see whether it has anything to do with this. So we do the same thing. This is our ggplot. This is the data set. What do we want on the X and the Y? So this is what we want on the X and Y. And then we have the box plot. So that will draw us the first one. Okay. So you can see that that treatment, you can see treatment B. So what we are saying is that treatment B, plots that are treatment B, had a higher starting point. They had higher biomass compared to the rest. So that is likely also going to have an effect on the yield, because if you're starting with a good biomass, you may have higher yield compared to somebody starting with a lower biomass. So this is the the kind of information that we are going to have, and it's going to help us to see how the relationship build up. Remember yesterday we said if you drew a model and in that model you have something missing, and then you're likely to have a model that may not necessarily give you the right information. We are going to suffer issues of validity. Okay, so we do the same thing like we did before. First part, we even bring in the color. We do a box plot. We fetch it with a block, and then we have the title. So we can do this. Okay. Okay, so you can see here that our biomass. So now let's see. You see now treatment A on plot 1, it had the lowest biomass, but it also had the lowest yield. When you go to plot number 3, it had the highest biomass, and then it also had the highest yield. So we seem to see that the biomass seems to have an effect on the final yield. If we don't correct this into our final analysis, then we are going to have a model that is not going to be very, very useful. Okay? So now the question now we want to see is there a relationship between yield and biomass? Because remember, we are looking at the relationship between the treatment and yield. Now, if there is a relationship between biomass and yield, that is going to confound the relationship of interest. We want to see how does treatment affect yield. But it looks like if the biomass is different, the yield will accumulate differently. So we need to be able to control that in our model. The difference between a box plot and a ggplot is a ggplot is a function. Here, this is a function that can produce can also draw for you a box plot. This function here can also draw for you a box plot. They're just different functions. They all draw the same thing, but they have different design and have different outcome in terms of how beautiful the graph will look like. Okay, so what we want to do now is we want to see that there seems to be a relationship between the initial yield and the initial biomass and yield. So if that relationship exists, we should be able to remove that relationship before we can compare the different treatment. Because remember from here, we realized that where the biomass was low, the final yield was also low. Where the biomass was high, the final yield was also high. So that effect needs to be removed before we can make our comparison. So now we are going to change and draw another graph. So in this case now, we are going to do geopoint. So we're going to draw some kind of a scatter plot. And then after drawing the scatter plot, so this is what we can do. So this part here alone, so you can see here that if the initial mass is low, the yield is also low. So it seems to see a straightforward straight line relationship, a linear relationship between the initial biomass and yield of the crop. And this is likely to have an effect on the comparisons of the treatment that we have. Now we can also put a straight line or regression line here by using this part of the model. G-smooth method equals to LM, which is the linear models. Okay, so if we run the whole thing here, so you can see now for each treatment, we are trying to run a different model. So from here, we need certainly to control for the initial biomass. Otherwise, if we don't control for the initial biomass, we are going to have a relationship that may not be authentic. We check if there are some questions that needs. The certificate, now for me, I'm only interested, I'm first giving you the knowledge. The certificate, we'll talk about it later. Yes, Jolene, there are some two people with their hands raised up. I don't know if you can promote one of them. Not Jolene, Selma.
Promoted to come back.
Okay, so let me stop. Okay. I want to ask question. Can you ask question you want to share?
Can you hear me?
Yes.
I said I'd like you to help us install the ggplot package because I run my script and it doesn't work. It said that you can't find the ggplot package. I don't know.
But when you go up here, did you see line number 5? Okay.
Yeah.
So did you run line number 5?
Already, but
after installing, then you need to run line number 9.
Okay.
So if you don't call the library, it will not come. So apart from installing, you also need to call it.
Okay. If I select all the script from 1 to 10 and I run it,
no, if you've already done the installation, then you need to run. If you've already done this, before you can use any of this package that you've installed, you need to run these ones as well. Okay. So you should be okay with that now. Yes, Mona?
It said here, please, it said here that the package is not available on this version of R. I don't know.
Which version of R do you have?
Of 4.5.1.
You should be having it. When you try to do the installation, what did it say? Okay, can you share your screen?
Yes, sir.
Okay, you share the screen.
Yeah.
Yeah, you could be having a poor connection.
So it says here that the package ggplot is not available for this version.
No, I'm not sure that is going to. Can you do the installation again? Run that line 5. I want to see. You don't need to highlight. You just need to click. Let the cursor be on any of on the line there. One or more package. No. You're ignoring. You should not run. I think you have the package. Just run line 10. RStudio is okay. So can you go and run the ggplot command and see whether it will work?
Okay.
Okay, just run one of them. Yeah.
Yeah. Now it's working.
Okay. Okay, good.
Thank you. Thank you.
You can stop sharing. Yes, so Fatia.
Fatia, please migrate. Okay, you can start sharing the screen and unmute.
Yeah. Hey, but it's not accepted.
Katia is already in the panelist room. Is that
okay. Can you share the screen and we see?
Can you share the screen?
Or if you just have a question to ask, you can ask.
She seems to be having problem with her audio connection. I don't know if she's able to share. Can you share the screen?
Can you share and we see? Say there's problem with line number 12. Now we are in line number. Okay, I think we're going to sort that one out. Step 12, well, fine. I think that's okay. Maybe, okay, let me go a little bit to, so I'm trying to build a story here. So we see from here that there is a strong relationship between the initial biomass and yield. So before we can compare the yield of the different treatments, we need to correct for the differences in the initial biomass, and that is what makes this becomes analysis of covariance instead of analysis of variance. Okay, so we can, let me see, geo. So we can also draw some histograms. So in this case, you use the geo histogram. So you can see for the histogram, we don't have the X and the Y, we only have the X. So the yield can be the X-axis. And then here you can specify how many bins you want to have. But for now, let's just run here and we see the result. So this is what we want to see, whether there is a normal distribution of yield. We can also go and draw more or less what called, instead of for yield, we can also draw for the biomass. So you see, they seems to have different kind of structure. Now, if you want to know the actual distribution, you can also proceed and draw a density plot, which in this case is we use geodensity. And then you can show the distribution of the different treatments. So here you fill using treatment. So here, the first thing is you have the GG plot, and then the first part will draw for you the X axis. So we can go, it gives you the biomass here. And then if you add the second part, which is you add this. Hey, what is this saying? Okay, let me run the whole thing and see. Okay, so this is what you have kind of. So we can see the A is somewhere there. You have the D is this one. So here you can see whether they have similar means or they don't have. I mean, we talk about a normal distribution. So we seems to have this one here with some kind of a nice shape. but you can see this one has more than one, but we can't read much into this. So that's the first thing that we have done here. We've done some exploratory data analysis. So from the exploratory data analysis, we have realized that there is actually a strong relationship between the yield and the biomass that we need to take into consideration if we are to come up with a good model. If we don't do that, then we are going to have a bit of challenges. So what I want us to do briefly in the next 2 minutes is to, I think my colleague can continue running, or we can continue running this tomorrow. So the thing is, we can then fit different models. So here, we are going to use this function LM. LM simply going to fit a linear model. And then what kind of relationship do we want? Remember, we talk about yield as being our response variables. And then we want to take care of the effect of the treatment. We want to take care of the effect of the block. And then this is our data. So in this analysis here, we are not taking into consideration the biomass. We are doing our normal analysis of variance. Now, in the second model, in addition to taking care of the treatment and the block, we are also taking care of the biomass. So then this equation here, then this becomes an additional component. So this is our normal analysis of variance. This is then becomes analysis of covariance because we have added the covariate to our analysis. So we can run these two models. And then, so what we do in R is you create an object. Now, this object that you've created, you can do many things with it. So we've created one object, which is we call mode 0, which is for our first model. And then the other one is mode 1, which is for our second model. And then under this, we can get a summary for the model 1. Okay, so you can see here that for our model 1, so the result tells you that we did a linear model, and the relationship we are looking at the yield, we are relating it to treatment and block, and this is the data set. So this is our model. This part here is our model. When it comes here, then the model will have the intercept. Remember, we talk about the general mean. The model will have the intercept. Okay. Then the model will have the effect of treatment B. The model will have the effect of treatment C. The model will have effect of treatment D. Now, we don't have the effect of treatment A. The effect of treatment A is in our intercept. Then we have effect of block 1, block 3, 2, effect of block 3, effects of block 4, and then the effects of block 5. Okay, so you can see from here, this one tells you that the intercept is significantly different from, so it's significant with 3 stars. So here is the interpretation. Okay, you can have at 3 stars, that is significant at 0.01, 0.001, 2 stars at 0.01, 1 star at 0.05, a dot at 0.1, and then 1. So the extreme is the probability of a 0, and the other extreme is the probability of a 1. And then here it gives you the residual, the degrees of freedom. It gives you the R square, which tells you how good a model is. And then we have this. So this is for our model number 1, or model 0. And model 0 does not have our initial biomass in. If we look at our model number 2, So you see that model number 2 is different. You have the intercept, you have treatment B, you have treatment C, you have treatment D. Now, but there you can now see that these things are now significant, but when we did not adjust, it was only the intercept that is significant. So you already see that there is a big change in the results. So the blocks are all, these are all, so you can see that actually the biomass is actually significant. So there's a strong relationship between the biomass and yield. So you can see that by excluding the biomass from the model, we have two separate models. And this can actually be very, very misleading in the kind of conclusion that you're going to draw. So these are still the same, but you can see now this model here, the R square is 0.98. Which is explained about 98% or 99% of the variability. This one only explained about 64% of the variability. So if you don't specify the correct model, you're likely to end up with completely different results. Of course, this is going to affect many things. You can look at the different means. You can look at the different values that we have there. So maybe just let me run this. So here we can then estimate the means. So we have two means here. If we use the first model without, this mean is not adjusted. It is only adjusted for the block because this randomized complete block design. Now, if you run with the second model, this one will take care of the covariance. So you actually will see that the effect of the means will change because of the use of the covariate. So let's run estimate for model 1. So what you can see here is that this is the function. Then you need to determine, you need to put in the model, and then you need to put in in this case, the treatment, what you want to estimate. So we can run this. We can run this. We can run this. Now, what I want to do is I want to combine the two together. What I want to do is I just want to pick the information from model 1, information from model 2. I bring them together so that we are able to compare them. Let me first clean my screen, and then, so you can see from here that if you don't adjust, the mean is 33.2. If you adjust, the mean is 34. If you don't adjust, for B is 39, almost 40. If you adjust, it's 36. For C is 31. If you adjust, it's 32. And then this is 35. If you adjust, you get a 36. So you can see now that you have two different models that they're giving you two different estimates. Okay. One takes care of the covariate, the other one does not take care of the covariate. And this also changes if you're going to make pairwise comparison from the two model, you'll actually see completely different results as well. So if we compare the means from the first model, so you can see if you compare the mean from the first model, if you compare mean A and B, you see the p-value is not significant. For it to be significant, the p-value has to be less than 0.05 if your alpha is that. So you can see here, A and B are not significant. A and C are not significant. It's only, this is almost significant at 1%, 10%. But if we look at the one of the second model, so you can see now A and C significant, B and C are significant, C and D are significant. So we are able to demonstrate two things, that the effect of the covariate and also the effect of not not specifying the model correctly. So that is what will have. So I think we want to stop here, but before we stop, we wanted to, Selma, we shared our brochure. So we have, let me first stop sharing this. We have a small company that we do training, we do support students in data analysis. So we shared a brochure with you, and we expect that you can reach us whenever you think we need. We can do for you. If your institution wants the training, maybe Ruforum has been very generous, has been offering you training for free. But I don't think with the current economy, the free treatment is the free thing is going to continue for so long. So we may need to try to get something into our pocket. So we have this small company that I think we share the brochure with you. You can read our vision, read what we stand for. And this is our colleagues, Ellen is here. So any of your needs we can we can sort out. So at the moment you can reach us through the emails. That is Tafiti Data consultants@gmail.com. Our website is still not yet running, but our emails are here. Our phone contacts are here, but I think for now it would be good if you can send us this. Yeah, so this one I think has been included in the material for the. The other thing I want to repeat is that we are planning to organize a Q&A session on experimental design. So we are going to share a link with maybe tomorrow, and from that link you can fill out and put in some questions that you think we should address. And then once we have the questions, then we are going to fix the day together with Ruforum so that we are able to have maybe 2 or 3 hours to address the queries with you. So I think maybe my colleagues can say a word or two, and then we give you back to Ruforum. So I can stop and allow my colleagues to. Yes, Ellen, can you say a word or two? Ellen?
Maybe she's not there. Okay, let me talk.
Okay.
Tomorrow you continue.
I can come in a little bit.
Good afternoon, good evening, participants. Thank you for being patient with us, and I hope you are gaining from the sessions so far that we've had. I would like to thank Thomas for taking you through this afternoon. He will come in tomorrow a little bit, then probably somebody else comes in with something else. But we believe that you people are gaining, and you'll be able to, the knowledge that you've received will be able to help you do your analysis independently and be able to complete your thesis or write a publication on time. Thank you very much, and I would like you to send messages to Dr. Thomas, thanking him. I can see them in the chat. Thank you so much for thanking Dr. Thomas. He has done a great job, and would like to hand over to Ruforum in case there's something to say. Okay, Ruforum, Selma.
Thank you, Prof. Thank you very much, Prof. Just want to also give a very big round of applause to you.
Selma, you are muted, I think.
Yeah. It's okay. You are the one who's.
Oh.
Yes, Prof, can you hear me now? Thank you very much, Prof. And the team for really taking us through this session and for your patience in going through each and every problem. We really appreciate your support and for always willing to do this. Participants, we also want to thank you for your patience. We want to hope that we'll continue to have you here tomorrow. Also, in addition to the announcement which was just made, some of you might be on the African Plant Breeders Association platform, and there is a webinar also starting right now. I see many of you have been dropping since when the time clocked. So you can always join in because information is power. Thank you very much. See you tomorrow at the same time. And please do catch up on the YouTube channel and visit the link for the folder with the document so that you try to be up to date tomorrow in case you missed anything in today's session or yesterday's. Thank you and have a good evening.